Lecture 4, the Chinese Postman problem and graphic sequences. Recap of previous lecture. In previous lecture, we have discussed eulerian circuits, fundamental parameters of the graph, that is vertex degrees, counting, extremal problems, and so on. Content of this lecture. In this lecture, we will discuss one application of eulerian circuit, that is the Chinese Postman problem, and then we will go and discuss graphic sequences of a graph. The Chinese Postman problem deals with the routing problem. So, the routing problem are concerned with finding the ways to route the delivery of the goods or the services to an assortment of the destinations like mail or garbage collection. In this particular problem setting, we require a graph which is called a weighted graph. The edges are assigned the positive numbers called weights. These weights can represent the entities like distances, time, and costs. The Chinese Postman problem is the problem of finding a tour that covers all the edges of the weighted graph, and that is the optimal, that is of the minimum cost. These problems are the generalization of an Euler circuit problem that we have seen in the last lecture. The real life applications. There could be a road network which must be travelled by a mail carrier delivering mails to the building along the street, and a snow plow which must clear the snow from each lane of the streets. A highway department crew must maintain each street, the police patrol car which makes its round through all the streets several times a day. So, the optimization of covering all these streets with a minimum cost is an important task for all such real life applications. So, in each case a person or a vehicle must travel each street at least once. So, in the best situation where every road intersection, that is the vertex, has a even degree, no retracing is needed. In such case, any Euler circuit solves the problem very effectively. But it is rarely the case that every vertex in a road network is even. So, how are we going to solve the Chinese Postman problem in that problem setting? So, a mail carrier must traverse all the edges in the road network starting and ending at a post office. The edges has non-negative weights representing the distance or the time. So, we seek a closed walk of minimum total length that uses all the edges. Hence, this is a generalization of the Euler's circuit. So, Euler circuit is a closed walk which does not have the repeated edges, and that is why it is a closed trail containing all the edges called Euler circuit. We require that circuit which is having the minimum total cost, and this is the Chinese Postman problem. So, this is the Chinese Postman problem named in the honor of Chinese mathematician Gao Magu, who proposed it in 1962. Application of a Chinese Postman problem we are going to cover here in this part of this particular lecture. Now, if every vertex is even, then the graph is Eulerian, and the answer is to the Chinese Postman problem is the sum of edge weights in the graph. Now, if it is not, then we must repeat the edges. So, every traversal is Eulerian circuit of a graph obtained by the duplicating the edges. So, finding the shortest traversal is equivalent to finding the minimum total weight of the edges whose duplication will make all the degrees even. Now, when we say duplication, then if we use a edge 3 or more times in making all the vertices, even the deleting 2 of these copies will leave the all vertices yet even. So there are many ways to choose the duplicated edges, and that becomes an optimization problem. So Chinese Postman becomes an optimization problem. Let us see through an example this Chinese Postman problem and the optimization issues involved in this particular Chinese Postman problem. So in the example below, the 8 outer vertices have odd degrees. So they are basically, this is an odd degree vertex, this is an odd degree vertex, this is an odd degree vertex, this is also an odd degree vertex. So there are total 8 such odd degree vertices present in this particular weighted graph. Now you know that the Euler circuit, this is not an Eulerian graph. Why? Because all the vertices has to be of even degree here, which is not. So if we match them around the outside to make the degrees even, so we have to pay an extra cost. So how to make this particular graph, which is having an odd degree vertices, as an Eulerian graph? By duplicating such that the total cost of the tour is minimum. So here if you see the duplicate, how to make the edges duplicate so that this graph can convert it into a Eulerian graph. So the first way states that we have to match the vertices around outside to make the degrees even. So these two vertices, for example, they are odd degree. If we match this particular edge of length 4, then you see that these degrees will become even then in that case. Similarly, if we match this, if we match this, if we match this. So in this particular graph we have added 4 different edges, and all these edges are of cost 4. So the total weight extra cost comes out to be 16 here in this particular method. Another method, if we take these 2 vertices and add an edge of cost 1, then they will become even. Similarly, here also we can add an extra edge. Now here also we have to add to make these 2 even and these 2 even off. So these duplicacy will make the second method incurring an extra cost as 1 plus 7 plus 7 plus 1, that comes out to be 16. Now there is another method which we can do better of these 2 methods. And which says that all the vertical edges, if we include, then the cost will be reduced. So vertical edges will include, for example, this particular vertical edge. If we add, this will add a cost 1. So this particular vertex will become even, but this particular vertex will become odd in this case because it was earlier even. Adding one edge will become odd. So we keep on adding another edge to make it an even. Now this will become odd. So again we have to add one more edge. So this particular vertex will become even. So this particular vertex also will become even. Similarly, to make this particular vertex as even we have to add these extra edges of length 1. What about these two vertices? We have to add an edge over here, we have to add an edge of cost 1. So, if we sum them 1, 2, then 3, 4, 4, 4, 8, 9, 10, that method 3 will give an extra cost as 10. So, this becomes this method 3 basically will require a minimum cost to make this particular graph as an Eulerian graph. So, the earlier total weights, total cost of a tour will become the weights, edge weights of the graph G plus this extra cost, and hence having converted this particular way, this particular Chinese Postman problem can be solved. This optimization problem we can solve here in this particular problem setting. So, let us recall what we have so far done in the previous example. So, adding an edge from an odd vertex to an even vertex makes the even vertex odd. So, we have to keep on doing it. So, we must continue adding the edges until we complete the trail to an odd vertex, and that particular process, when it completes all the vertices, will become even in that case. The duplicate edges must consist of the collection of the trail that pairs the odd vertices. Edmonds and Johnson in 1973 described a way to solve the Chinese Postman problem. If there are only 2 odd vertices, then we can apply Dijkstra's algorithm to find the shortest path between them and solve the problem. Now, if there are 2k odd vertices, then use of Dijkstra's algorithm to find shortest paths connecting each pair of odd vertices. Use these lengths as the weights on the edges of these 2k odd vertices and find the minimum cost weight of k edges that pair up these 2k vertices. This is the weighted version of the maximum matching problem. So, this way we uses the, instead of direct edge, indirect edges are applied. Why? Because when we apply the Dijkstra's routing algorithm, shortest path algorithm, it will find out a shortest path between 2 odd vertices, and that particular shortest path will be added up, whether it is a direct edge or it will be a path connecting the 2 vertices. So, this way this Chinese Postman problem can be solved with the help of, if a particular shortest path algorithm is available, then this particular graph, given graph, can be converted into an Eulerian graph, and these extra duplicacy of the edges, which can be solved with the help of Dijkstra's algorithm, can be utilized in this particular process. So, let us see the Chinese Postman algorithm. So, step 1 is to list all the odd vertices that we have shown you in the previous example. Then, after finding out all the odd vertices, second step would be to list possible pairing of odd vertices. The third step would be that each pairing will find the edges that connect the vertices with a minimum weight, either Dijkstra's algorithm will solve it. Why? Because if the graph is of big size, manually or cannot inspect and find out these minimum weights, you have to apply the Dijkstra's shortest path algorithm. Step number 4 would be to find the pairings such that the sum of the weights is minimized. So, in the original graph, you have to add those edges that have been found in the previous step, that means with the edges with the minimum weights. Now, the length of an optimal Chinese Postman route is the sum of all the edges added to the total, which is found in step number 4. So, this way up to step number 6 we could find out what is the total cost of an optimal Chinese postman route. Now, we have to find out in step number 7 the actual route, means how the postman basically should traverse along the edges, so that it will incur the minimum cost in that particular route. So, the route corresponding to this minimum cost can be then easily found out by tracing those edges starting from at one point. Let us see this particular algorithm working through an example. So, here we have a mail carrier has to deliver the mail to all the streets in the subdivision. The mail carrier has to start and end point at A, where the post office is located. The weight of each edge is represented, represents the length of each street, which is most efficient route for the mail carrier in this particular problem setting, and we have to basically show with the help of that algorithm which we have stated, that Chinese postman algorithm. So, in this particular problem setting, the first step is to find out the odd vertices. So, B, C, D, E, which is encircled here, they are the odd vertices. So, B, C, D, E are the odd vertices. Second step would be to pair them, these are pairing of these odd vertices. So, how many possible pairings of B, C, D, E are there? One pair is B, C, the other pair is D, E, this is first pair, second pair is B, D and C, E, this is second pair, third pair would be B, E and C, D, this is the third pair. So, there are 3 different pairs possible. Now, we have to find out the shortest way of joining the pairs using the path. So, B, C, B and C, they can be reached with a direct edge of cost 3, but if we go by some other way it will become more costly. So, obviously B and C, they can be connected with a minimum cost of 3. Similarly, D, E also can be connected with a minimum cost. So, total cost of adding these edges would be 7 here in this particular case. That means, if we add an edge of cost 3 and if we add an edge of cost 4, so this particular total cost will be of this particular entire graph, and all the nodes will become even Eulerian, will require an extra cost of 7. Now, another pairing which we have to see is BD, B and D. So, B and D have a direct edge of cost 5, but if we come along A and then from A to D, then the cost will be 3. So, we have to basically add an edge of a cost 3, and 3 star means it is not a direct path, but indirectly we have to come in this way. So, basically an edge of length 3 is added over here. Similarly, CE, there is a direct edge of length 6, but if we come along F, come through F, then basically the cost will be 3. So, let us add an edge of cost 3. So, this will make the graph Eulerian and will incur only the cost of 6 units. Similarly, we have another pairing, that is BE and so BE. So, BE do not have a direct edge. So, it has to come through via A. So, when it will come via A, it will incur 7, but when it will come through C, B, C, F, and then basically it will cost, so it will become a cost of 6. So, you can see, so 3, then 3, 6. So, it will, so if you add an edge BE of a cost 6, and which will basically obtained via F. So, that is why 6 and E star is given. Similarly, CD, there is no direct connection, but if you come via B, A, D, that incur a cost of 6. So, total cost here 6 plus 6, that becomes 12. So, out of these 3 combinations, we see that this is having the lowest cost or a minimum cost to convert this graph into an Eulerian graph. Hence, we will choose this particular, that is BD of an extra cost 3 and CE of an extra cost E to solve this particular problem. Now, the extra cost is 6 here in this particular case. So, step number 4 would be to draw the edges onto this particular graph. So, we have basically traversed through these edges. So, let us add the extra edges to connect this BE and CD. So, having added these edges, we have completed the step number 4 of the algorithm. Now, step 5 says that the length of the optimal Chinese Postman route is the sum of all the edges in the original graph, which becomes 24, and extra edge cost, which we have found out in step number 4, is 6. So, the total cost is 30. And the next step would be to find out that particular route. So, let us see how to find out that particular route. Here in this case, we start from A, then we go to B, then from B we are going to C, and from C we are going to F. From F we have to go back again to C, and from C we have to go to E, and from E we are going to F, and from F we have to come back to E again, and from E we are going to D, and from D we are going to B, and from B we are going to A, and from A we are going to D, and from D we are coming back to A again. So, we started from A and we have reached A traversing all the edges exactly once. With the total cost 30. So, this is the solution of a Chinese Postman problem. Graphic sequences. So, a degree sequence of a graph is the list of vertex degrees, usually written in the non-increasing order as D1 is greater than or equal to D2, greater than or equal to D3, and so on up to Dn. So, this particular way we can state here the degree sequence of a graph. So, degree of vertex, so highest degree is W, then followed by W it will be X, then followed by X it will be Y, then followed by Y it is Z, and followed by that it is V. So, this is a degree sequence of a graph. Now, another question is, if we are given a sequence like this, now the question is whether this is a degree sequence of a graph or not. So, given a graph G, it is easy to find out its degree sequence, but given a sequence of a non-negative integers like this, when is it a degree sequence of some graph? If this sequence of non-negative integers represents a degree sequence of a graph, then it is called a graphic sequence. So, how do we find out this particular case whether this sequence of non-negative integers is a degree sequence of a graph or not? That is called the degree sequence. So, we have to see a proposition to basically come out with a particular strategy to basically test whether the given sequence is a graphic sequence or not. Proposition: the non-negative integers d1, d2 and so on dn are the vertex degrees of some graph if and only if the sum of all degrees is even. Let us prove this. First we have to see the necessity condition. So, in the necessity condition, let us assume that some graph G has these numbers d1, d2 and so on up to dn as its vertex degrees. So, if we apply the degree sum formula, then this sum of all the degrees will be the twice the number of edges in the graph, and this particular value, the parity of this particular value will become even. Why? Because it is multiplied by even number, hence the sum of the degrees is even, and one side of this particular theorem or a proposition is proved. Let us see the other side of a theorem, that is the sufficiency condition. Here in the sufficiency condition, we will assume that the sum of degrees is even, and so we have to find out. So, sufficiency condition, let us assume that the sum of degrees is even. So, we have to basically find out the statement, that is d1, d2 and so on are the vertices of some graph. So, we have to construct a graph with the vertex sets v1, v2 and so on up to vn, and dvi is equal to di for all the vertices I. Now, since this sum of degrees of these vertices is even, the number of odd values is even then in that case. In the previous slides, this particular result we have already seen. So, first we form an arbitrary pairing of the vertices in the set of odd degrees of vertices, and for each resulting pairing form an edge having these two vertices as its endpoints. The remaining degrees needed at each vertex is even and non-negative. Satisfy this by each I placing a di by 2 loops at these vertices, and hence we can produce a graph out of it, shown that the given set of integers d1 and so on up to dn are the vertices of some graph. Graphic sequence. Graphic sequence is a list of non-negative numbers, that is the degree sequence of some simple graph. A simple graph realizes d means a simple graph with a degree sequence d. For example, here 1 1 3, if this sequence is given, then we can inspect quickly and tell that this is not a graphical sequence. Why? Because here we can say that 1 2 3, the odd vertices, the degree of odd vertices, here it is a odd number. For any given graph, the number of odd vertices is always even, hence this is not a graphical sequence, or this particular sequence does not represent the degree of any graph. Let us take another example, 3 and 3. 3 and 3, they are not graphical sequence. Although these particular odd vertices are 2 in number, that means they are even in number, even then it is not a graphical sequence, because there is another condition which says that the maximum degree here, which is called a 3, it should be n minus 1 at most, and that is n minus 1 means only 2 vertices are there. So, n minus 1 is equal to 1. So, the maximum degree should be 1, but it is 3. So, obviously it is not the degree sequence of any graph. So, out of this particular examples, we have collected up some of the obvious conditions, that degree sum must be even, and also the degrees must be at most n minus 1 for all i's. Although these conditions are necessary, but they are not sufficient. For example, we can see a 4 vertex node having the degree sequence 3 3 3 1, whether, so here you can see that, so n is equal to 4, so the maximum degree is 3, so 3 is basically allowed, and the degree sum is 10, that is also an even number. So although this is obvious conditions are, that is the necessary conditions are satisfied, but it is also not sufficient that this sequence is the graphical sequence. Let us see how. So basically let us see this particular vertex. So we can place an edge like this, so it has consumed all 3 degrees. Now what about these other 2 vertices? Let us say this vertex, whose degree is now 2, can connect, let us say, 2 other vertices, then only its degree will become 3 and it will be exhausted. This particular node has the degree 2, still it has 1 degree remaining. What about this? This node has basically exceeded its degree 2, hence this is not possible to make a graph out of these particular degree sequence, hence it is not a graphic sequence, hence the sequence is not graphic. So we have seen that although the necessary conditions are satisfied, but it is also required to be sufficient condition. Here the sufficient condition is failed, hence this particular sequence is not basically graphical. Another observation is that the graphic sequence, for example, this particular sequence represents a particular graph, more than 1 graphs. So it does not matter. So that means at least 1 graph it should represents to satisfy that it is a graphic sequence. Now this particular graphic sequence, where necessary and sufficient condition both are required to be satisfied. So we will see how this particular, both the conditions are to be evolved and how they are going to be satisfied, and for that we are going to see a theorem. But before that, let us see some of the background why the theorem is required, where necessary and sufficient condition both are required to be satisfied. So let us see this particular list, 2 2 1 1 and 1 0 1, they are graphic. So if this is graphic 1 0 1, so 1 0 1 means that it is a k2 plus k1, this is k2 plus k1, this represents 2 2 1 1 graphic sequence. Now this particular graphic sequence, if we add a vertex to it, w, like this, and place a edge to this particular node, so what will happen is another vertex w, whose degree will be basically 2, will come. So another node w will be added, its degree is 2, and this degree will be increased to 2, and the 0 degree will become 1. So it is nothing but the same graphic sequence which we have obtained. So this we have seen that there is, by recursive conditions, if one graphic sequence is basically given to us and we obtain another sequence through that particular sequence by adding a particular vertex and the edges, then if we obtain another graphic sequence, this is a recursive way by which we have to prove that this a particular sequence is a graphic sequence or not. Similarly, to test whether this is a sequence 3 3 3 2 2 1 is a graphic sequence or not, so we seek a realization with a vertex at w. Let us take a vertex with the highest degree, and its that many number of neighbors. For example, degree is 3, so 3 neighbors, 1 2 3, and then if we delete this particular vertex and remove the degree and reduce the degree by 1, we will obtain another sequence. Let us see whether this sequence is graphic or not. So we reorder it and then we will continue doing it. So 3 is the highest degree and 3 of its neighbor we choose, and once we delete it, we will obtain 1 1 1 2 2 1. So, if we reorder them, it will become 2 2, this becomes this sequence. Now, we have to check whether this is a graphic or not. So, we have to choose this particular vertex, 2 its 2 neighbors we have to choose, and if we remove it, so it will become 1, it will become 0, then 1 1 1. So, if we reorder it 1 1 1 1 0. So, we have to check whether this is graphic or not. So, 1 1 1 0, we can see whether this graph can be drawn out of it or not. So, 1 2 3 4 1 2 3 4 and 1. So, this will represent a particular graph. So, hence this is a graphic sequence. If this is the graphic sequence, we can add an edge to it and place the vertices like this. So, this also will become graphic sequence, and this particular on this particular sequence, if we add an edge, we will obtain this particular sequence. So, this sequence is also become graphic. Hence, this is a recursive construction by which we can prove that this whether the given sequence is a graphic sequence or not. The entire thing is illustrated here in this particular picture that I have already explained you. Now, with this particular background, a theorem is given on this particular graphic sequence, and this theorem is given by Havel and Halimi. So, the theorem states that for n is greater than 1, an integer list D of size n is graphic if and only if D prime is graphic, where D prime is obtained from D by deleting its largest element delta and subtracting 1 from its delta next largest element. The only one element graphic sequence is D1 is equal to 0. So, let us see the proof. So, for n is equal to 1, the statement is trivial. So, for n is greater than 1, we have to prove the condition is sufficient. To prove the condition is sufficient, let us assume that we are given a D with D1 greater than or equal to D2 and so on up to Dn, and a simple graph G prime with a degree sequence D prime. We add a new vertex adjacent to the vertices in G prime with the degrees D2 minus 1 and so on D delta plus 1 minus 1. So, these Di's are the delta largest elements of D after one copy of that delta itself, but D2 minus 1 and so on up to D delta plus 1 minus 1 need not be delta largest element in D dash. So, we can see here that D is given D1, D2 and so on up to Dn, and D prime which we obtain is basically nothing but the D2 minus 1, that is if we remove D1 and that delta plus 1 minus 1, that particular delta number of elements, we have to reduce its degree 1, and after delta plus 1 all the up to Dn, all these particular degrees are not basically touched upon. So, that is nothing but D prime. Now, to prove the necessity, so that was the sufficiency condition. Now, we have to prove the necessity condition. In this necessity condition, we have to begin with the simple graph G. Realizing D, we produce a simple graph G prime which is realizing D prime. So, in the sense, what we are proving is, if we are given a sequence S of D, so if we can obtain another graphic sequence D prime from it, then this is the graphic sequence. Or if we have a graphic sequence, then if we place a vertex and if we can obtain D, then basically it is also a graphic sequence. So, here S prime is given, and if we place an edge. So, both ways we are going to prove. Now, here we are given a graph G which is realizing D. So that means a graph G is given and we can sequence its vertices according to their non increasing degrees. So we produce after that, using that, another simple graph G prime realizing D prime by removing that particular edge. So let W be the vertex which is having highest degree in delta, and let S be the set of delta vertices in G having the desired degrees D2 and so on up to D delta plus 1. Now if this NW, that is neighbors of W, is S, these set of vertices, then we delete that particular W and we obtain G prime in this particular manner. This is pretty straightforward. However, if they are not, basically if neighbors of W is not these particular set of degrees, but some other degrees are there where some vertex of S is missing from N of W, then in that case we have to modify this particular G and we will increase this neighbor of W intersection of S without changing any vertex degrees. So this neighborhood of W intersection S can increase at most delta times. Repeating this converts G into another graph G star that realizes D and has S as the neighborhood of W. Now from G star so that means if the maximum degree node does not have its neighborhood NW provided in S, then we can basically swap, or a two switch operation we have to do. One node we have to remove out of S and another node which is basically there, should be there, will be entered it and make it the case like the previous case here, and then we can go ahead for the deletion. Let us see how we are going to do this. So let us see that if W is the vertex D1 and delta vertices which we are basically considering, but here these are not the neighbors of S, that means there exists some vertex which is not according to the order which should be here, it should be on the other side. So to find the modification when N of W, that is neighbor of W, is not equal to S, we choose X which is in S and an element Z which is not in S, so that W and Z which are adjacent, but W and X are not adjacent. So we obtain in this case this particular edge which is given here in this particular case present, but the elements which is not in S, that is called X, is not present, and this edge is also not present. So we will do a two switch operation. In this two switch operation, what we will do, that we want to add Wx, this is to be added up and will be introduced in basically N of W, and we will delete Wz, but we must preserve the vertex degrees, since degree of D of X is greater than degree of Z, and already W is the neighbor of Z but not of X, there must be another vertex Y. So if X is entered and W and Z is removed, so another vertex has to be there, and that is Y which is adjacent to X but not to Z. Now we delete Wz and Xy is also to be deleted, and add Wx, this we have already added, and Yz z also is added. So, having done that, we will basically increase NW, and now the NW will become equal to S. In another way, we can understand that a particular degree, let us say, take the example 3, 3, 3, 3, 1. So, in this particular example, what we see is that 3 and its 3 neighbors are having degree 3, 3, 3. If it is not, for example, if we place this particular 3 here and 2 is over here, then this particular degree sum, that is the sum of the degrees of 1, 2, 3 is basically, this becomes 8, and which is less than, if you consider this as 3 degree, that is 9, that is when it should have been in this particular condition, then this particular degree sum will become 9. So, in any case, if the degree sum is less than some other vertices which is not present in this n of s, sorry, n of w, this is w, neighbor of w's, then we have to apply the 2 switch operation, and that is why we have to call it as reorder every time. So, 3, after this reordering, it will become 3, 3, 3, 3, 3, 2, 1. Then this particular 3 will have its 3 neighbors in this basically non-increasing order of the degree. So, here it is not, it is violating the non-increasing order of the degree. So, we have to reorder the operation, and in this theorem we have seen the application of a 2 switch operation. So, once it is done in this particular form, then we can apply, that means we remove this w, and basically we can reduce the number of vertices. How many times? D delta plus 1 minus 1 we have to do, this become 2, this become 2, this become 2, and so on. Then again we have to reorder it. So, reordering is important operation, and that we haven't seen how that is being basically covered here in the sufficiency condition of the proof. So, necessary and sufficient condition both are required, we have already seen in this particular proof of graphic sequence. Now, 2 switch operation we have used, let us briefly explain it. A 2 switch is the replacement of a pair of edges x, y and zw in a simple graph by the edges yz and xw. Given that x, yz and wx did not appear in the graph originally, so we will switch it, we will exclude these particular edges and we will include these 2 edges, and this is called a 2 switch operation that we have already used in the previous theorem. Now, if y and z they are adjacent, or w and x is adjacent, then 2 switch cannot be performed, because the resulting graph would not be simple. The 2 switch preserves all the vertex degrees. If some 2 switch turns h to h star, then a 2 switch on the same 4 vertices turns h star into h. So, the dashed lines above indicate non-adjacent pairs. Now, we can see here in this particular illustration that 2 successive 2 switches operation has transformed this particular graph into this particular graph, and hence it will preserve the vertex degrees as we have already mentioned. So, conclusion, in this lecture we have discussed the application of eulerian circuit, that is a Chinese Postman problem, which is an optimization problem in many applications, and also we have seen the graphic sequence and a particular theorem, and in this particular theorem we have seen the necessary and sufficient, both conditions are required to basically test whether a sequence is a graphic sequence or not. In the upcoming lectures we will discuss the concepts and properties of a trees and distance. Thank you.